Well, that's one way to interrupt recycling of materials, that's for sure. Now we've got Dr. John Haddock, Materials in Aerospace, Composites and Lightweighting. John is the Head of Materials Engineering Disciplines at BAE Systems. John joined British Aerospace at Filton in 1990, where he worked in materials and processes before becoming the project manager for advanced metallic wing R&D activity. And in 2002, he moved to BAE Systems military aircraft, again to lead materials and product integrity. And throughout his career, he's been closely involved with UK and European research activities. So we look forward to hearing from John on aerospace. John, thank you very much.
Okay, so good afternoon everybody. When I was requested to do this presentation, my initial thought, well, it's not a problem. We've got lots of really interesting materials research going on. Some of it around some of the subjects that have already been talked about today, around nanomaterials and that. But when I found out the timescale that I'd get to get all the approvals in place before I came to do this, I realised that it wasn't going to be quite as easy as I thought. So I'm not going to be able to talk to you about some of the materials development work we're doing around morphing structures, where we can actually change the shape of composite materials by applying a potential. I can't really talk to you about some of the stuff we're doing about composites using nanomaterials so that they can store electricity or become part of the electrical systems of the airframe. Some of the things we're talking about, where the car body becomes the battery for the thing. So I won't be able to talk to you about those. And I know I definitely won't be able to talk to you about the things we're doing on materials to reduce the aircraft signature and improve the sort of stealthiness of our products. So what I thought I would try to do was really to talk about really from my perspective, the fact that it's rare that it's a material in its own right that offers a lightweighting opportunity all on its own. So if we go back to the 80s, we had aluminium lithium alloys.
It's been a theft of the substation.
I think there's something come up here about something about user account control. So anyway, when we were in the 80s, we had aluminium lithium alloys, which we okay now? Yeah. We had aluminium lithium alloys which offered some good property opportunities, 10% weight reduction through density, 10% increase in stiffness, all fantastic properties, but most of that was never really realised. There was a lot of effort put into it, but it never really got utilised and it never got into general use. Today we have the main commercial airframers using a lot of the new third generation aluminium lithium alloys, which don't really offer the same property benefits that the old aluminium lithium alloys offered. I think the density reduction is about 5 to 6% on some of the new ones. So the question is why? Why is aluminium lithium alloys now being picked up, whereas in the 80s, when they were offering probably more improved properties, they didn't? And I think the key really is I've moved on a slide and that hasn't. Try something else. Oh. I don't know what's happening here.
Just give me a second.
Sorry, which way am I going here now? Which are the arrow things? Or just using page down?
This is the what were you pressing? Whatever you pressing before?
I was just pressing the arrow key.
Yeah?
Yeah. Yeah. So the key, sorry, the key is that the difference now is the combination of both the material properties and the processes that allow those properties to be effectively utilised in design to give the benefits that you really want. And in reality, aluminium lithium alloys have been introduced on the A380, been extensive use of them in the new A350, which is coming along from Airbus, and the Bombardier C-series aircraft also contains quite a lot of aluminium lithium alloys, and I'm sure Boeing are doing similar things. So the difference really is that we've been able to utilise the material, not just the material properties, but the processing. The material is more processable than the old type of alloys were, and they're actually offering now up to a 25% weight reduction over the conventional aluminium alloys, which is helping, although the picture we saw earlier this morning, a big portion of an A350 is composite now. The aluminium element has been maintained through the introduction of some of the weight reductions achieved with the aluminium lithium alloys. From a composites point of view, the sort of things that we're trying to do is to use the composite materials in a more effective way. And one of the things that we're doing is looking at the creation of bonded composite structures. We've used composite bonded structures for quite some time. The sort of co-curing type thing that you do when you build a carbon fibre composite structure. But those kinds of bonding activities require a lot of very complex tooling. They require autoclave processing, and that obviously adds a lot of cost and a lot of complexity to the process. In addition, you can't make closed structures by that process. So what I really wanted to talk about now was the new generation of paste adhesives. The real material innovation is in developing paste adhesives. So that's the little, very small material development, better paste adhesives, and where we can then use that to achieve a lightweighting in the structure. The other way we've conventionally done adhesive bonding is by using film adhesives. Now, film adhesives are very thin. They, by nature, because they're just a film, they only stick where they touch structure. And although a designer can draw a very nice picture that shows a spar with some skins attached by a paste adhesive, in reality, the surfaces that come together are not quite as straight as you'd like them to be. And excuse me for my very crude graphics here. As a materials engineer, I'm a very poor draftsman. But in reality, the surfaces that you're trying to bring together are not exactly flat. To get a good film adhesive bond, you need to maintain flat surfaces in the range of about 0.125 of a millimetre. And that's really very difficult to do on large structures. So to be able to do film adhesive bonding, what we first have to do is put some kind of liquid shim into any undulations or any disparities in the surfaces that we're trying to bond. And then we'll try and machine that off and try and get it completely flat. And then we'll put our film adhesive in, and then we'll put in a whole load of complex tooling to maintain the pressure and the bond gap. And then we'll cure it and make a good adhesive bond. But then, in the end, for whatever reasons, and then they're often called chicken rivets, we'll still drill them and put a fastener in just to be on the safe side. So what this does is actually create a very complex process with more weight in it than it really needs. Because as soon as you put a fastener in there, the thickness of the skin is designed around the fastener and the fastener pull-out loads rather than the adhesive bond. What we'd really like to do is to move to something that's much simpler. So we have uneven surface, we fill that gap with a paste adhesive which has the ability to flow and make good contact with all the surfaces that it's mating with, that we can actually work to a gap that is probably 3 times that we try to work to with a film adhesive, and thus we can start to get some real benefits and simplify the whole process. So if we can move to that kind of bond, we can get a thicker bond line which eliminates the need for all that shimming and all those processes. If the paste adhesive is offering us the properties that we're hoping that they're going to offer us, we've got increased confidence in the adhesive bond, so we can start to eliminate those fasteners. Once we've eliminated the fastener, that allows us to use thinner skins because we're not designing around the pull-out loads and the bearing strength of the material around the fasteners. Once we've eliminated the fastener and we've reduced the skin thickness, we're now getting our weight reduction. Because we don't have to try and control our bond line to the same degree that we did before, we've now can eliminate a lot of the very expensive tooling that we've been using for our other bonding methods. By removing the fastener, we're also reducing aerodynamic drag, increasing endurance for the aircraft because we've taken weight out, and something that's probably a bit more peculiar to military aircraft than anywhere else, we start to reduce opportunities for radar signature. But, and there's always a but, isn't there, with all of these things, there are some key enablers that we need to put in place. The first is really the development of the paste adhesives, and we're working with other adhesive manufacturers to develop those properties. We need to be able to be very confident in the joints that we develop. One thing about the aerospace industry is we have to feel very confident that everything has been tested, verified, and that we repeatedly get the same strength of bond time after time after time. So one of the only ways you can do this with adhesive bonding is to start to automate the process. So you're really controlling the process very carefully. So we want to automate the surface preparation. What we really need is something to be able to look at that surface and tell us whether it is really clean. And that's a whole another subject of what does clean mean and how do you analyse a surface to see whether it's clean. And then something that applies the bond paste adhesive in a very consistent manner so that we get eventually our high quality bonded joint. But having done all of that, and it doesn't matter how confident we are in the control of our process, we'll still be wanting to inspect it when we've finished. So we need some non-destructive inspection techniques to be able to look at those structures. And this is something that's really exercising the minds of our NDT engineers at the moment. A lot of the techniques that we conventionally use, ultrasonics, X-ray, eddy current, don't really have the resolution to be able to tell us whether we've got a good joint or not. They're often confused by just intimate contact. So you might have intimate contact, which conventional process might say you've got a good joint, but you haven't really got the adhesion that you think you've got. And finally, we need some structural analysis techniques. Once we can start to use these kind of paste adhesives, we'll be able to look at different design concepts for the joints. But to be able to do that, we need some structural analysis tools so that we don't have to go away and do structural testing of every possible configuration that we can think of. So the overall benefit really is a better application of composite material into an aerospace structure. So we can use some more innovative designs. We can reduce part count by eliminating fasteners and shims and all those things that I talked about. We can reduce section thicknesses by removing those fasteners and therefore reducing mass and being able to reduce costs because we've taken away a lot of those tooling aspects that I talked about. So the final outcome really is more efficient structures, reducing weight and cost of manufacture, the application of more innovative design, and then the ability for us to be able to produce what our customer wants. You know, the pictures here of unmanned aircraft with either long endurance, lower fuel burn, stealthier structures. Those are all the things that our customers are demanding of us at the moment. And through this kind of application, we'll be able to provide. I think the final message from me really was that for every material development, there also needs to be a lot of the research into industrial processes to enable its use in practice. It's the sort of thing that was mentioned in the keynote speech really about how do you look at those material developments and have the processes to actually make them into the big things that you really want to make. And I think that's me finished. Thank you.